Hello and welcome to the channel. My name's Vincent and I'm coming to you from the UK. You can find me on X at Vincent Gledhill. Now, right off the bat, I've got to say I'm not a doctor and none of this is medical advice. This may be the ramblings of a madman. Cancer is a mitochondrial metabolic disease. It is not a genetic disease, as proven by Professor Thomas Seyfried and his team at Boston College. And as a cancer survivor, I understand his message. It's my mission in life to spread the truth and save the world. And once you wake up and see the light, I'm sure that you'll want to join me in saving humanity from this dreadful disease. You can support the channel on Patreon with links in the description. Now, with that said, let's get into it. So, do you want to die? Serious question. Now, you're going to say, oh, yes, of course. Of course I don't want to die. Well, my Auntie Anne, when she was ill in hospital, she actually did want to die. She'd had enough. She didn't want to see any other. She didn't have anything left to see, were her words. So, if you do want to live, well, stick around, because I've got a lot of videos lined up from Professor Thomas Seyfried on why cancer is a mitochondrial metabolic disease. And first of all, let's have a look at how it starts.
Yeah, so, the definition of cancer, and I may have mentioned this before, is cell division out of control. So what happens to the first or group of cells that become dysregulated in their growth? Because ultimately, this is what the problem is. You have most of the cells in our body are in what we call a differentiated state, a quiescent state. They're all arranged in order in our various organs and tissues, and they all contribute together to the society of cells in the body, which ultimately is us. Whether it's in the brain, the liver, you have liver dysfunction and your brain responds in a way. The brain would have a problem. The liver would respond in a way. All of our systems are integrated through blood networks, through immune systems. So we are actually a very highly tuned, integrated machine. What happens, though, to a cell in, say, a breast or a bladder or a colon or lung, that would make that cell become dysregulated in its growth? So, there's been a lot of ways that cancer has been produced in cells and tissues of our body, and most of it has to do with a chronic disruption of the cellular microenvironment through irritation, through a viral infection, through a blocked blood vessel that would cause a chronic or restricted hypoxic environment. The problem is that and I say chronic because most acute damages to cells and tissues will lead to rapid death. And as Otto Warburg said, you can never get a dysregulated cancer cell from a dead cell. So there has to be some time frame when this regulated cell, this quiescent differentiated cell, has an opportunity to become dysregulated. And what's responsible for the quiescent regulated differentiated state is the function of the energy metabolism within that cell. And that's controlled by the organelle called the mitochondrion. It's kind of a spaghetti network that exists in the cytoplasm of the cell. That network interacts with the nucleus. The nucleus and the mitochondria within a cell have a very intimate communication system from signaling pathways and such like this. But a chronic insult to a cell or a tissue leads to a gradual loss of energy through oxygen. So to prove that, I mean, you're breathing, I'm breathing, most living people, most animal, everything gets energy. They breathe oxygen, get oxygen in, either through the gills, through the lungs, or whatever. That oxygen serves as an acceptor, a final electron acceptor for the electron transport chain in the mitochondria that generate large amounts of energy very efficiently. However, if that energy efficiency is chronically interrupted, not to the point where you kill the cell, because if there's no energy, death, you can't be live with no energy. So what happens in the cancer process is that the energy is transferred from oxidative phosphorylation, breathing oxygen, to an ancient pathway of what we call fermentation. The technical term is substrate level phosphorylation, a type of energy mechanism that existed for all living organisms.
Oxidative phosphorylation. Quite a mouthful there, but basically that is the cells breathing oxygen. We breathe in and out. We breathe, and it's damage to those cells themselves.
Yeah. So I mean, the definition from oxidative phosphorylation, breathing oxygen, to an ancient pathway of what we call fermentation. The technical term is substrate level phosphorylation. A type of energy mechanism that existed for all living organisms that were on our planet before oxygen came into the atmosphere some 2.5 billion years ago. So these heirlooms of energy metabolism exist in most of the cells of our body, these old ancient heirlooms, but they play a very, very minor role when we're breathing oxygen. They have a very low production of energy. If these OXPHOS, energy through oxidative phosphorylation, is corrupted or deficient or anything like that, the ancient pathways are upregulated, and the mitochondria send a message to the nucleus of the cell, and the nucleus of the cell sends out a messenger that upregulates transporters for glucose and glutamine, the two fuels that are necessary for these ancient pathways to maintain viability. The problem with that is that that same organelle, the mitochondria that's responsible for differentiation and quiescence, also controls the cell cycle and the differentiated state. So when that organelle becomes corrupted and the cell falls back on the ancient fermentation pathways, the controller of the cell cycle is not there. And what happens? The cell starts to divide exactly the way it did 2.5 billion years ago, because all of the cells at that time were dysregulated in their growth. They just grew and grew and grew and grew until the fuels, fermentable fuels, disappeared in the environment, and the cells would die. So this whole cancer thing is not a mystery. These cells are simply falling back, these cancer cells. And when you look at them, in every major tissue of every major cancer, you look at the mitochondria in the human cells, and you find them defective. You find them few in number, their morphology is abnormal, and their function is abnormal. So if that's all abnormal, and structure determines function, then these cells are dividing and dysregulated because the very organelle that's controlling this process is dysfunctional. And these cells then are growing based on the availability of the sugar glucose and the amino acid glutamine in the microenvironment of those cells. And as long as those two fuels are present in sufficient quantities, those cells will be growing in a dysregulated way, and they become worse and worse and worse until you get the spread, which we now know what underlies that. That's another story that would require some level of explanation.
So there we have it, damage to the mitochondria. So with the current system that we've got, where they're all searching, looking for genes. So let me give you a little example. They're currently looking for genes. So we're all running around wearing pink. Not me, I hasten to add, but you know what I'm saying. So let's imagine that you're playing hide and seek with your 7-year-old son. And you're in the kitchen and you count to 10. 1, 2, 3, 4, 5, 6. Come in, ready or not. He's hiding under the bed. Okay? He's upstairs, hiding under his bed. But you search in the kitchen, you go in the first kitchen cupboard, the second kitchen cupboard, you look all over. He's not there. So you look behind the sofa. He's not there. You look in the cupboard under the stairs. He's not there. You look in the lounge. You look behind the sofa. He's not there. You look behind the chair. He's not there. You look in the cupboard. He's not there. Now, imagine they've told you that children never, ever, ever hide upstairs. So you don't go upstairs. So you phone the police. My son's gone missing. We're all out wearing pink, running around the parks, raising as much money as we can for you to chase around downstairs, not looking in the right place. That's exactly what we've done with cancer. We are looking in the wrong place. The damage to the genes are downstream epiphenomena. And if I can find the video where Professor Thomas Seyfried explains such, I'll put it on next. I found a video about biopsies. Biopsies themselves can actually spread the disease. So let's take a look at that.
So, and they already know some of these diagnostic breast mammograms, they can put people at risk for further spread. Biopsies and all this kind of crazy stuff that they're doing is, why are you doing a biopsy? Oh, I have to know if you have stage 1 or stage 2 or stage 3. Well, if you had stage 3, well, you would never want to stick it. And if you have stage 1, you stick it, it could become a stage 2 or 3. Why are you doing that? Well, we do it because we were trained to do it. Would you ever think about, oh, I didn't know about that. You read the damn literature, for Christ's sake. These people don't read the scientific literature to show what they're doing can put these people at risk. I can't tell you how many oncologists. I did a big interview with Peter Attia. He said, Tom, you shouldn't be saying things like this. It's not science. I said, what do you mean, Peter? I said, for Christ's sake, do you read the literature? Well, I didn't see those articles. The standard of care was never written in granite. It's only supposed to be used because based on best medical practices and outcome, it should be used until something better comes along. Something better is here, but why now can you not use it? Then you have to say, oh, there's something other than patient outcome that must be underlying the lack of ability to use this new approach to managing cancer. So that becomes a different level of investigation. You know, why they don't want to do this.
Why indeed? Do you have any ideas? Please leave your comments in the description. Please leave your comments below and let me know. What do you think?
The standard of care was never written in granite. It becomes a different level of investigation. You know, why they don't want to do this? What are the real reasons for not wanting to do this? And I told you at the beginning, there's a number of reasons why people can't do that. The hospital administrators, you have to look at bottom lines and budgets and all this kind of stuff. I mean, you're going to bring in a treatment protocol that's not going to generate the revenue that you got from something else. Then we got to reevaluate whether we want to do that or not. People say, wow, are you sure about that? Go ahead. Go find out why you can't use metabolic therapy as a standalone next to, oh no, can't do that. Why? It doesn't go through the institutional review board. We have a group of physicians on institutional review boards that have to make the decision. They'll allow metabolic therapy under certain cases as long as it's done concurrently with the standard of care. The standard of care is your problem. So you got to get rid of the standard that's not working. The standard of care for brain cancer, at least for glioblastoma, is not working. It's not working for advanced lung cancer. It's not working for advanced breast cancer. It's not working for a systemic metastatic cancer. The
standard of care is not working for most cancers. Professor Seyfried talks a lot about glioblastoma, and he talks a lot about glioblastoma because the standard of care has nothing to offer glioblastoma patients. So let's hear about the politics of cancer.
You could be shut down because you're not following standard of care for political reasons. It has nothing to do with the clinical. They're shutting it down because they don't understand it.
Politics.
They don't know
what about
it.
The patients?
But because you're not following protocol, I mean, these poor, as you said, some of these poor guys could lose their license for doing it. You will not see metabolic therapy discussed in any degree at the top medical schools. You got to deal with they never heard of Otto. Many of them never heard of Otto Warburg. Many of them never heard of what I'm talking about. So you have that wall of interference. Yeah, it's a problem. Okay, so how do we get the word? You got to train physicians to know how to use the strategy, the technology. They have to be educated. They can be. This is not insurmountably. Some of the actual into the nitty gritty biochemical pathways supporting what I am saying does take a lot of in-depth knowledge and research. There's no question about it. I'm just able to take it out of the molecular mud and bring it into a comprehensible strategy. But I'm in the mud all the time, trying to clean up what we know and how to improve what we know. But we are already far enough along in case reports and in preclinical outcome to know this is the path forward. We already know that. So if we know that, why are we not going in that direction?
Why are we not going in that direction? Well, really, really tough one. Like he says, the system's broken. But for me, if it was me and I was diagnosed, the cancer had come back. I have had cancer, and yes, the standard of care did save me. There's no doubt about that. But why are they not doing it? Well, if you're a patient yourself, one thing you can do is you can do half of the metabolic therapy. You can do, and as I said, none of this is medical advice. I'm not a doctor, but you can do half of the therapy. You can do the diet, the ketogenic diet. So let's see what Thomas has to say about the keto mojo and the ketogenic diet.
We use the glucose ketone index calculator, which we published here. That gives the patient, every patient with cancer can then know how they stand. So it's a meter. You can buy it on Amazon, a Keto Mojo glucose ketone index meter, a meter that measures blood sugar. You prick your finger like a diabetic would. You measure with a strip. You can measure your blood sugar. You put the strip in the meter, reads the sugar. Okay, squeeze your finger a little bit more, put the ketone strip, put that in the meter. It tells you what your ketones are. You push the button and you get a ratio of how much ketone to glucose is in the blood. And normally people would look at that right after their lunch or dinner or whatever, and you'd have a value of about 50 or 60. Okay, to manage cancer, you need a value of 2.0 or below. Okay, people say, oh man, I don't know if I can get that. They eat this and, oh, can I eat that? Can I eat this? I don't know. Why don't you check your GKI, your glucose ketone index, and see whether you can eat that? And they said, oh no, it went up to 20. Well, don't eat that. So it's not that hard. And then they'll come and say, oh man, it's really, really hard to get my blood sugars down and my ketones up. And I said, well, I said, you want to kill cancer cells? What's your plan here? It's not easy. I don't want people to think, I'll tell you, it's a hell of a lot easier sitting down in the oncology thing and getting infused with poison. You don't have to do anything. You just sit in a lounge chair and they just drain it into your bloodstream. Doing metabolic therapy requires a big part, a big emphasis, effort on your part. The patient has to play a major role in the management of the disease. Otherwise, it's not going to work. So when
Absolutely. The patient has to play a part, otherwise it's not going to work. So going on the ketogenic diet and getting your blood ketone levels at the GKI at 2.0 or below, which is what the professor recommends.
we use the glucose ketone index, then the patient becomes, now the next step is use specific drugs that work better against the glucose and glutamine together. So you got the diet on the one side, making you healthier, putting pressure on the tumor cells, but then you hit them with low doses of a variety of other, and some of that can be low dose chemo, by the way. And then you just start hammering these tumor cells out of existence. So, and degrade them slowly while you continue to be healthy. None of this hair loss, vomiting, and all this other stuff. The tumor cells cannot survive in these harsh metabolic environments. You're doing it by lowering your sugar, and then you take small doses of like repurposed drugs and things like we already listed some of these, and more of them are becoming recognized. So you don't need to spend a lot of money. Now, as I said, you don't need to suffer with a lot of toxicity. Is it easy? No. If I know what I'd have to do, but do you think I'm going to be saying, oh, no, I can't eat donuts and rice and bread? Okay, well, that might be the part of your sacrifice. And what a lot of people do, they dovetail it in with prayer. Whatever religion they are, they pray, and that helps them avoid bread. And in other words, it gives them more motivation to participate in their own healing process. What we found is that the human body has incredible capacity to heal itself if given the opportunity. So when you give your body the opportunity to heal, it will heal. It's hard to heal when you're being irradiated and treated with drugs that are poisonous. It's hard for the body to rally against that. So I think we have to change this whole paradigm by the way cancer is treated, and we can get much better success than what we have currently today.
So if you're going to do a ketogenic diet and get your GKI, how do you get it down to the level of 2.0 or below? Well, here is a demonstration by some random guy on the internet on how to get your ketones down.
All right, so first thing I want to do before I stab my finger is open up the strips. So the blue is the ketone strips, and this takes 9 seconds to measure, okay? And if you think that's fast, I actually kind of come to think it's kind of slow.
Apologies to a random
so I like
guy
to have
on
my
the
strips
internet.
ready to go.
I
So I've got
shall
my
give you
ketones
a
measure
shout
strip,
out. I'll
and
find
then I've
out
got
and give you a
my
shout out in the next
my
in the next live
glucose. The
session.
brown is going to measure my blood sugar, and I like to have these out so that I can easily put them in the device and use one prick of blood. I don't want to prick my finger multiple times. So here's what I'm going to do. I'm going to put the glucose in first with the blue strip down, and it goes into the keto meter here, and you'll hear it kind of click. Well, there you go. There, it kind of clicked there. So it tells you now that it's ready to measure glucose. So what I'm going to do is I'm going to load the finger prick, and I'm going to kind of let it start to bleed. And what I do is I push the blood up to it. I get a nice big bulbous, because I want this to be enough for both the strips, okay? So the first thing I'll do is I'll just let that blood touch the strip, and you'll see it's 5 seconds. And I'll get a reading of 67, which is not bad considering I've been fasting all day and I just had a CT scan. Now we're gonna measure, okay, so I'm trying to keep the blood on my hand kind of like fresh, and I'm gonna put the blue strip in, and now we're gonna measure ketones. It's gonna take 9 seconds, and I just kind of licked my finger here, All right, 2.5 for the day. So this is really good. Now, here's the thing. These numbers by themselves are great, but the app on your phone brings them all together and allows you to see like your tracking. And if you don't have the Keto Mojo app, just go to the App Store and grab it. When I open up the app, immediately I'm coming to my readings. the first thing that I'm gonna do is I'm gonna click the sync button on the lower right-hand side. And what that does is it syncs with this device. So this device has to be on in order for this to work. And what'll happen is the last 4 readings, okay, are imported. I'm gonna click on the check sign and I'm gonna scroll down and I can see that 8:31, which is today, at 4:41 p.m., I have a GKI of 1.4, which is really good. That's where I wanna be. My glucose, you can see it in the brown, is at 67, and my ketones are at 2.5. So it's exactly the numbers that you saw here. But the app does a mathematical equation to give me a GKI, which is my glucose ketone index.
So, as you can see there, the guy explaining how to do the GKI measurement with the Mojo Keto Mojo. So that's one half of the metabolic therapy. Sorry, I just looked around there and yeah, I saw the stream disappear off YouTube, and I thought it was just me with the flick backwards and forwards of the thing. So I'm just having a look for more videos of Professor Seyfried. Metastatic cancer. So how does it spread?
That's another thing, metastasis, which is the singular most complicating factor of cancer. Because if all tumors grew in place, we would just cut your arm off or cut whatever, and it's gone.
Cut your arm off.
But it spreads. So how does it spread? What's going on with the spread? So what we discovered was an interesting kind of cancer in the mouse. It came out of the brain spontaneously, but when we put it in the flame, it spread like wildfire throughout the whole body of the mouse. And then it took us 10 years of vigorous, constant research. What kind of a cell?
10 years.
What is that cell?
10 years.
What kind of a cell is this thing that spreads all over the body? Because this is what is responsible for the majority of cancer deaths. So we found out that it was it was a macrophage, a microglial cell, which is derived from macrophages in the brain. It's a localized thing. So a macrophage, huh? Wow, macrophages are the only cell that can move in and out of our tissues. So we have resident macrophages in all of our cells. They're residents, they're like a police department. And then we have white blood cells circulating through our bloodstream, and that's like the army. So when you have a stab wound, white blood cells come out of the blood and they transform into these macrophages, and they're there to kill bacteria, clean up the wound. They're very fusogenic. They fuse together to work and heal the wound. In the cancer, what we have is that there's an inflammatory group of cells, like chronic inflammation, hypoxia, whatever, causing what looks like a wound to the body. So the body sends in the immune system. If the local guys can't handle it, the immune system, and they throw out growth factors and cytokines to heal the wound. And what that does to a cancer cell, like a stem cell, that doesn't have the capacity, it just grows in place. It makes them grow more. So these immune cells fuse together with these other kinds of destabilized cancer cells that have mitochondrial abnormality, and they're growing but they can't spread. They're not. But this cell has the genetic apparatus to already move in and out of tissue. So when that cell fuses with this other cell, now you get destabilized mitochondria in a cell that's programmed so it becomes a rogue macrophage moving in and out of the cells. Wow, this is like unbelievable. So how do I know this? Why would I tell you this if I didn't know what I was talking about? So we went through every major cancer that we know of and examined genetic readouts of macrophage products. Every major human cancer has all of these characteristics of macrophages. So they all started from this procedure. The late John Powlick at Yale University was screaming at the top of his lungs, this is a fusion hybridization between macrophages and cancer stem cells, producing this metastatic cell that can now readily spread throughout the body. So after we made this discovery that nobody believes because they're locked into this mindless genetic thinking. Yep. So first thing you say, what do macrophages eat? What's their fuel? What do? They'll eat anything. but they gobble up stuff and they bring it to their lysosome, and then they can get energy from what they do. But one of their prime fuels is glutamine. Macrophages in the immune system are driven by glutamine. Aha!
Aha! Aha!
So then we found they're fermenting the damn.
Aha! Aha! So there you go. Metastasis. A hybridization of a macrophage with a cancer stem cell. So, he's done the work. They've done the due diligence. As you heard there, 10 years of trial and error on mice to find out exactly what causes metastasis. And it's not oncogenes and boncogenes and woncogenes. It's a rogue macrophage. So let's just take a look at one more video.
So we just have taken Warburg's concept, polished it all up, and now can explain clearly what the origin of cancer is. Once the cancer field comes to understand this, then they have no choice but to target glucose and glutamine simultaneously. It becomes the obvious and clear pathway for managing all cancers. And this is another thing that gets everybody all upset. They think breast cancer is different from colon cancer, different from brain. They're all very, very similar. They need those fuels to grow. They can't use oxygen. That's the similarity. They're all genetically different. They look different under the microscope, but they're all similar. They need fermentation, target the fermentation, and you can manage this disease. So that's the bottom. When you get enough people that respond well, healthy, didn't lose their hair, didn't get all this toxicity, and their cancer, very deadly type of a cancer, goes away, more and more people will want to do that. And that it just takes time for the field to come to recognize this.
As I said earlier, it's my mission in life to get this message out to more and more people. My mission in life. Now let's have a look what the probability is of great outcomes with the current standard.
Problem with cancer cells is how they generate their energy for growth. That's the key. You have to realize without energy, nothing can grow. Cancer cells divide rapidly. They grow out of control. Everybody knows this is what it is. The definition of cancer is dysregulated cell growth or cell growth out of control. So you have to say, well, where's the energy coming from? Where's the energy coming for a cell to grow? And the answer you have to say is that I said you could get energy from oxygen, or you can get energy without oxygen, which is called fermentation, ancient pathway of fermentation. Cancer cells can grow rapidly without oxygen. So where are they getting their energy? And they get their energy from evolutionarily conserved heirloomic pathways. That's where they're getting their energy. So when we say cancer is a metabolic disease and not a genetic disease, we mean that the dysregulated growth is coming from disturbed energy metabolism, and that the mutations that you see that the field seems to be obsessed with are all downstream epiphenomena. So if the field is focusing on a downstream effect, the probability of making major breakthroughs in the advancement and management of the disease will not happen in fact, they won't happen. So in fact, we're not going to make any major advance in cancer until it becomes recognized as a metabolic disease. Then you're going to see huge changes real quick.
We are not going to make any real changes until it's recognized as a metabolic disease. We are not going to make any changes until they recognize that it's a metabolic disease. Please help me get this message out. If you know anyone that's got a large subscribing YouTube channel, please get them to come on the channel and speak to me. I will explain to them all of what Professor Thomas Seyfried has said, all of what he does say, and try and get this message out to as many people as possible. What about the current oncologists? What do they think?
So they don't recognize cancer as a metabolic disease. When you realize that it's a metabolic disease and the mutations in the cancer cell prevent it from being, they're locked into a very tight fermentation. If you can't ferment, they're going to be dead, and they don't have the ability to adapt like the normal cells have. It all goes back to evolutionary biology. If you don't understand evolutionary biology, you do very stupid things, okay? Like immunotherapy, very stupid. So, and you do all these crazy things because you don't understand evolutionary biology. What are you supposed to do? You know, and unfortunately the field doesn't, they look at you like, you might as well be talking to a plug socket because they don't even know what the hell you're talking about. So, I'm telling you, it's terrible, right? All these guys, they talk like they know what they're doing. You know, no, Jack, if they knew what they're doing, why are they doing this crazy stuff to these poor cancer patients? So you see how it all comes together? It all comes together because I understand evolutionary biology. And when you understand that, you know how to, that's so many nice ways we can kill cancer cells without toxicity. You just exploit their weakness, their metabolic weakness. And when you realize how many ways we can kill cancer cells without toxicity, it's just so almost infinite once you understand the system. So it just takes time.
It just takes time. So, what's this? That is information from Cancer Research UK. Cancer Research UK reckon that 10 million people will die worldwide this year from cancer. And today being, what's the date today? Sometime in February anyway, 12th of February. And as of today's date, that is the amount of people that have died so far this year from cancer. 1,165,155 as I read this message. Absolutely, absolutely unbelievable. Sorry, I'm new to this streaming malarkey and all my keyboard presses to try and get the right screen up. And it's been a marvellous day. I've had one viewer online, so thank you to that one viewer. Just hope it wasn't my mate who said he might check in, but he is busy working today, so yeah. Hope it wasn't him. But I will do another live stream tomorrow, and hope I get better at the whole job. Thanks for that. And if there are any questions, please do leave them in the comments below, and I can address them in tomorrow's live stream. And until then, bye bye.